So let's look at some data here and see the Clausius-Clapeyron equation in action. Notice what I'm doing is I'm plotting vapor pressure here versus temperature. And as I do so, I will notice a couple of things. First, there's my exponential growth that's occurring, just like I wanted. Also notice, though, that the point at which this exponential growth occurs changes. It continues to move over to the right. And the reason it does so is because this is where my delta H term figures into it. My delta H value pushes me in this direction. Notice that it takes water sitting way over here the longest to finally explode up in vapor pressure because it has the largest delta H of vaporization. On the other hand, something like diethyl ether, which is a nice, almost symmetrical kind of hydrocarbon, has a very, very high vapor pressure because its delta H of vaporization is very small. In all the cases, though, I still have that exponent to the minus delta H over RT relationship playing out. So the functional relationship looks exactly the same. There's that temperature in the denominator showing that exponential increase, and there's that delta H term, which is pushing when I start to see the exponential increase exhibiting itself here. All right, I now have a way to be able to do this kind of plot in which I can stick in a value for a temperature for a particular delta H, and it's going to give me a vapor pressure out. That's kind of useful to have. You can read delta H vaporization values in the back of the book. You can stick in a temperature. Out comes your vapor pressure. But there's something kind of neat that I can do with this that you'll see rising up over and over again. That's the idea that I can predict, given one temperature and vapor pressure, for a new temperature, another vapor pressure that will result. This is called the combined Clausius-Clapeyron equation. So as I look at this combined Clausius-Clapeyron equation, you'll see that what I've done to be able to create it was to take that e to the minus delta H over RT term that we talked about, and I eliminated a value that was constant between the two of them. In particular, I eliminated that delta S of vaporization. By eliminating it, I was able to combine, rearrange, and create this equation here, which says that the ratio of the vapor pressures is equal to this delta H of vaporization times this 1 over T1 minus 1 over T2 term. So this right here is the combined Clausius-Clapeyron equation. How might I use it? Well, if I happen to know what the heat of vaporization is for water, I know it's about 40 kilojoules per mole. And I happen to know one temperature, for example. I know that water, for example, has a temperature at about 20 degrees of 17 torr. I can, for any other temperature, predict a new vapor pressure. So to prove that this is the case, let's take some particular temperature here and try to predict what the pressure would be. Now, if you don't believe me about what this might turn out to be, let's choose something that you should know the vapor pressure for. I'm going to stick in the number 100 degrees here, and I'm going to do this calculation. What is it that I should predict when this is all done? What should I predict when this is done? Well, I know that at 100 degrees, that's the boiling point of water. And what is the vapor pressure at 100 degrees? Oh, it should be 760 torr. So when I do this calculation, what comes out the other side of it should be a value of 760 torr. Now the Clausius-Clapeyron equation is kind of clunky in the way it comes together because it has those 1 over T1 terms, and it's got that log term that you have to account for. You have to make sure that you get your kilojoules into joules. You have to make sure that your temperatures are in Kelvin. But having done all that, I'm going to rearrange and solve this problem that I talked about just a second ago. What happens if I start with a known value for the vapor pressure at 20 degrees, and that value is about 17 torr, or 2,300 pascals. Now, I am going to try to find a new temperature at the point where I'm at 760 torr. That's about 1 atmosphere. That's about 100,000 pascals. I stick in the value for delta H of vaporization that we've used a lot in this course. Not 40 kilojoules, but 40,000 kilojoules. I've got R here for the ideal gas law constant. All my units are working. I've got everything in the correct pressure units. I've got everything joules. I've got Kelvin. And now it's time to get my answer. The answer that comes out is 378 Kelvin. Not exactly right. I expected to get 373 Kelvin. I got 378 Kelvin, though, which is pretty darn close, and tells me that I'm at least moving in the right ballpark in terms of this calculation. Why isn't it exactly right? Well, if you remember back to the derivation of the Clausius-Clapeyron equation, the reason it got so simple in the first place was because I made two assumptions. I made the assumption that the free energy of a liquid was pressure independent, and I made the assumption that the change in entropy for an ideal gas was a constant across all different kinds of gases. Those two assumptions are not absolutely correct. And in particular, water, because of its stickiness, is going to have a very different kind of entropic process going on than other types of gas molecules. And as a result, we end up getting an answer that's off from what it should be. Not by a lot, but because of those assumptions, it is not exactly 373 Kelvin.